Assalamu alaikum wa rahmatullahi wa barakatuh. How are you guys?
وعليكم السلام
وعليكم السلام ورحمة الله وبركاته.
All right.
Fine,
So,
and you?
all right. Good. I'm still uploading the file to be shared. It is still converting. Only the second file is converted, so we will soon begin. But just to inform you, our lab for today. Okay. Our lab for today is going to be online, okay? But next week, that is when we have to come over physically to the lab, okay? So whatever we need to do today, I will schedule another online session during the lab time, and then we will all gather, and then we will take whatever material we need to take, okay?
Okay, Doctor.
All right.
Doctor, what about the quiz?
Okay, doctor, no problem.
All right. What are you saying, Abdulaziz?
What about quiz, Doctor?
What, doctor?
Yeah, why do you say we should postpone till next week? Because on our schedule we are supposed to have it every 2 weeks, and today is the second week.
Okay, doctor.
It's easy, Doctor.
No, I didn't. What?
Huh? It's easy, Doctor.
You need
The quiz,
what?
it's easy. I mean, the quiz, it's easy, Doctor.
I didn't prepare for it because some of you have started asking for postponement to next week. So I said, let me wait until we discuss about it and then see what to do. Okay. As for me, we can make it next week. Okay. But just so you know, you look at the schedule, it is supposed to be every 2 weeks. And I know you will have many quizzes every week like that. But the most important thing, you know, you are big guys now, is to start preparing well ahead of time. Okay. Just because you have another quiz doesn't mean you will postpone another one.
If we can make it online, Doctor, today, it's no problem.
Today is better because I have a lot of quizzes next week, and today I have a quiz. Tomorrow I have a quiz. It's on the time is not better for every quiz.
Yeah, but most of you like asked me to. Okay, we will discuss about it at the end because I wanted to have it today, but then you are like, let's make it next week. So why are some of you now objecting to next week again?
Doctor, let's take it next week, no problem.
Okay, we will talk about it so that it is still not loading. I think let me open it. Let me open the file and then share my screen with you. Yeah. It is not converting really. It is not converting the share application screen. So can you see the file?
No, not yet. Yes.
Yes now.
Okay. All right. So if you remember last week we have started explaining the what is hydraulics, what is hydrology, you know, and then what do you mean by water
We
resources?
talk, doctor, example 2.
Yes. So I'm just like giving you a recap, like an overview of what we did previously. Yeah. So we discussed about development of water resources, isn't it? Water resources development, where we looked at the quantitative aspect as well as the qualitative aspect. Okay. Now, the quantitative aspect dealing with water engineering and the qualitative aspect dealing with environmental engineering. Okay. And then the demand for water supply, we explained the 3 types of demands: withdrawal uses, non-withdrawal, and the consumptive use. By the way, who can tell me what is the consumptive use? Before we move on. Yeah, I can hear you.
But Doctor, what's the question?
Who can just tell me what is consumptive use? What do you understand to be consumptive use from your understanding of the previous lecture?
Doctor, about the lecture?
No, consumptive use. Under the water demand, I explained
Oh.
consumptive use. There is withdrawal uses, there is no withdrawal uses, and there is consumptive uses. So, what do you understand, about the non-consumptive use?
Doctor, when you take amount of water and use some of this amount and retain the
When you take
amount of water, for example, 10.
Doctor, Doctor,
yes.
when you have some water, we can use it again.
So where will the water go? How can we lose the water? How
like weather drawal, it's about maybe from 10 to 20 percentage about water we can't use it again, right?
Yeah, but I mean, how can we lose it? I mean, why does it become lost?
Oh.
I think the increase of the people, Doctor.
Increase of the people?
Yes.
What do
No.
you mean by increase of the people?
Increase
You
the
mean
people,
water
Doctor.
will-
The
number of
population,
people?
Doctor.
What?
The
If it
population.
is you,
It is used. Go ahead.
yeah, if it is used by industry or chemical industry, so we can use it again, maybe, or it has to like a hard treatment to be clear again.
You still don't get it. I said consumptive use. Let me just go over it.
Teacher, that is water
Is gross
demand.
quantity that is no longer available for further use, isn't it? It is used up by crops, humans, evapotranspiration, industrial processes. I give you example. When you take water, let's say you take 500 milli, 500 milli. Do you understand? You cannot urinate, you cannot excrete all the 500 milli. Do you understand? You may excrete, let's say, around 400 milli or 450 milli. But there will be some amount that your body, your cells, your body cells will use in, metabolic activities and cell growth and what have you, that cannot be excreted. Do you get the point? Can you hear me?
Yes, doctor, but
Yeah.
Yes, doctor.
So similar to crops, they need water for their growth. So when they extract water from the roots, that is buried inside the soil, some of the water they extracted from the soil is being released through what is called stomata. We will explain there are tiny openings at the underside of the leaves. Okay, so they excrete, they release the water through that. But then some of the water is used for their growth. Do you understand? So they cannot release some of the water they extracted from the soil. And that water that cannot be released back to the environment is termed as the consumptive use. Do you get the point now?
Yes, Doctor, yes, it's clear.
Okay. I saw some, okay. Water removed from available supplies without return to a water resource system. All right, so let's continue. If you remember, we even gave an example of the consumptive use where you have inflow minus outflow to give the consumptive use, okay? And then we look at population forecasting, because in water resources development, one of the most and the first important thing is to know the population that the water development or the water resources is going to serve, okay? So we need to project the population. Definitely, we know this curve, which we can explain the geometric growth, arithmetic growth, and the declining rate of growth. Okay, A to B is the geometric growth, B to C is the arithmetic growth. Okay, and then the formulations of each one, we derive them. Okay, and we solve example. Okay, is it clear? Shabab, is it clear?
Yes.
Yes, Doctor.
Yes, Doctor.
All right. So now we will look at per capita water usage. We will look at per capita water usage. Let me see if it has uploaded it, because it will be for beta 4. Try again. Okay, it has failed. Okay, so it can still continue. So per capita water usage. Okay, on the per capita water usage here, what we mean per capita is per person. Okay, per person. That is what the capita means. Capita equals with person. Do you understand? So it's the same thing as saying per person use. That is individual. How much water do you need normally in a day on the average? Okay, so it's normally expressed as the average daily rate, which is the mean annual usage. Mean annual usage of water average for a day in terms of gallons or liters, and it is indicated as per capita. Let me use the red pen here. Oh, it is still not showing what. Okay, let me use the blue one. Okay, so you have seen that LPCD, isn't it?
This is it.
Yeah, LPCD means liters per capita per day. L for liters, P for per, C for capita, and D for day. So that is missing per day. That is not shown there. Okay. So LPCD means liters per capita per day. Okay. Or you can make it, instead of using liters, you can use GPCD, which is gallons per capita per day, which is the average annual usage of water, average for a day. Meaning for the whole year, how much water do you need for the whole year? Because we know there is seasonal variation. The amount of water needed varies with season. Like now it is hot season, the summer. You need more water. You drink a lot of water. Okay. This is not the same thing when we reach the winter. During the winter, because the sun is not there, it is not hot. We are not, sweating. So we are not losing a lot of water at the time. So in that case, we don't need a lot of water. Okay, so the rate at which we drink water reduces. That is one. But at the same time, you will have to take care of other water uses. Like, once in a week, you take your car for washing, you wash your clothes. Every day, you take bath at least once, sometimes twice, sometimes even 3 times, depending on maybe you did something that made you, sweat very well. Do you get my point? So all this amount of water needed per annum, that is in 1 year, is now averaged over 365 days to get the LPCD. Do you understand? So now, the seasonal, monthly, daily, and hourly variations in the rate are given in percentages of the average. I explained the seasonal variation. There is also monthly variation, which also is tied to the seasonal sometimes. Because like sometimes, maybe when you are at home, you use more water than, when you go to work. So for that, when you are on vacation, you may use less water probably, or you may use more water. Daily, there is daily variation. Usually in the morning is peak hour, because everyone wants to take shower, to go to work, to go to school and what have you. And then the demand of water reduces, and then later in the evening, because people came back from work and what have you, they want to take shower, they want to do this, they want to cook, they want to do a lot of other stuff. So that increases the demand for water. So there is hourly variation. Okay, and all these are given in percentages of the average. Okay, deciding which of these should be used for the design capacity depends on the components of water supply system. Don't forget, Here, what our target in this chapter is to design, to have, to design the capacity of the different aspects of the water development scheme, okay? From the intake, the water intake, the treatment, the distribution, and all that, the pumps and what have you. So how do we design each of these components? So this is our target. But before we design the components, we need to know the demand. We need to estimate the demand. By demand, we mean the water needed by the community to be served. Is that clear? The community to be served the water, what is their demand? What do they need? Okay? And for us to estimate their need, we need to forecast, use the population forecasting. Now we are done with the population forecasting. The next most important aspect is the per capita water usage estimation. Okay? And an average value sometimes of 101 gallons per capita per day may be used. And sometimes, because when you convert this, it will be like almost like close to 400, or yeah, about 400 liters per capita per day. Someone may say, I don't use up to 400 liters per day. Yes, you don't use it per day, but sometimes if you take the average over the year, when you take care of the number of times you wash your car, the number of times you bathe, the number of times you wash your clothes, the number of times you use water, maybe sometimes to wash your house, your apartment, and all that, you will realize that the amount is not just a representative of the quantity of water that you drink. Is that clear? The per capita use is not related to the quantity of water that you drink, but the quantity of water that you use for whatever other purpose. For drinking, for bathing, for washing the laundry, washing your cars and what have you. So all that is put into consideration. So that is why you will see the amount to be somehow high. Do you understand?
All the water we are using for everything,
exactly.
Right?
Exactly. Now, the layout of typical water supply systems, okay? The layout of typical water supply systems. So I will explain this very well. Here you have a river, okay? You have a river here, okay? Or let me use the red. Yeah, the red will be better, I think, but let me increase the. So this is a river, okay? Which is our source of water in this case? You have the intake conduit. This is the intake conduit, which is extracting water from the river. And then this is another source. You can see well field, okay? You can have various wells. Like I told you, Afro-Bathing is supplied by about 14 wells, about 100 kilometers on Riyadh Road. Do you understand? So this is like a well field. Here you can, this is 6 in number, okay? So this is intake conduit. That is the pipeline, the pipe that conveys water from the well field or from the river to the treatment plant, okay? This is low lift pump, is the pump that will now pump the water into the treatment plant. Is that clear? It is called low lift pump. The pump that conveys water from away from the treatment plant to the conveyance pipeline or to the distribution system is called high lift pump. So understand the two differences. You have low lift pump and high lift pump, okay? Now, this is the treatment plant where the water is treated, probably for some things. You did CE 330 from the preliminary treatment. Maybe you can have flocculation, you have sedimentation, you have coagulation, you have filtration. At the end, you have disinfection. Okay, so all these are like some basic water treatment processes, okay? In 330, which some of you have done, or even if you have not done it, you have started doing it in this time, okay? You will learn all the various methods, all the various techniques of water treatment, okay? So this aspect, we will not touch it. That is left to the environmental engineering section. Is that clear? So when the water is treated, it is pumped by a high lift pump through a conveyance conduit, that is a pipe, okay, to service reservoir. Service reservoir here is usually, a tank, a very huge tank in the town, okay, that is elevated at high elevation. Is that clear? it is at high elevation. So from the treatment plant, the hydraulic pump usually pumps to this service reservoir, which is at high elevation, so that the water will flow by gravity from the reservoir to the distribution system. The distribution system here is like the town. In this case, you can consider the distribution system, you can visualize it to be the Hasselblad in town, okay? HB, okay? Where your house may be somewhere here, my house may be somewhere there. Is that clear? Do you understand? Oh, I will have to check to see your response. Okay, all right. All right. So now there are two systems of distributing to households, okay? One is by gravity. This is by T. By gravity here, it means you have a distribution, a service reservoir, which is like I said, raised above the ground level, okay? This is like a huge tank containing the water, okay? Raised above the ground level so that water can just flow by gravity. Do you understand? To the distribution mains, okay? Now, another way of sending water or of distributing water to end users is by direct pumping. Here in Hasselblad, we don't usually have the distribution, the service reservoir. What they do is pumping, direct pumping into the distribution system. By direct pumping here, if you realize all houses in Hasselblad, they have underground storage tank. They have underground storage tank. That underground storage tank, the water treatment plant will pump to the underground storage tank, and then individual houses will now install pump in the underground storage tank to pump water to the overhead storage tank. So each house has two tanks. You have the underground storage tank and the overhead tank, which is at the top, at the roof top. Do you get the point? So the water treatment plant, after the treatment plant will pump water to the underground storage tank of individual houses. And the individual houses will now install a pump that will pump the water from the underground storage tank to the overhead tank. And then the overhead tank will now supply all other plumbing system in the house. Do you understand? So in Africa here, we don't use service reservoir, but there is direct pumping. So the pumping is like the whole of Africa is like divided into zones, like maybe zone 1, zone 2, and zone 3. Let's say 1, 2, 3. Maybe today they will pump to zone 1, tomorrow they will pump to zone 3, zone 2, and the day after tomorrow they will pump to zone 3. And then like that, it will continue. So that, because like when you fill your tank, it is expected, to last you, let's say, a day or 2 or even 3 days, isn't it? So they divide it, they don't pump like 24 hours, 247. So they pump into this zone for some time and then shut this zone out, and then second zone, shut that zone out, and then pump to another zone. Do you understand?
Yes, doctor, yes.
Okay. Now, another method of getting our water source is from impounding reservoir. Impounding reservoir here refers to dam, okay? When you have water flow, like this is river, when you come here and dam it, by dam is just an embankment, okay? You place a barrier along the path of the flow, okay? You place a barrier, an elevated barrier, like a wall, isn't it? Dam is more or less like a very huge wall that is preventing the flow of water, isn't it? So that it will create a pool downstream, okay? So that water will now be stored, isn't it? Okay, so this is what is meant by impounding reservoir, meaning you create a dam and then you store water. When you store the water in the reservoir, you can now pump it using the conveyance conduit to the treatment plant, from the treatment plant to the distribution system. Is that clear? So here we are explaining two types of typical water supply system. The first one, which is this is the first one, and this is the second one. The first one is using a service reservoir, okay, which is an elevated tank in the downtown, so that water will flow by gravity. In the first one, the flow is from the treatment plant to the service reservoir. water is pumped, but from the service reservoir to the distribution system, the flow is by gravity. Is that clear? While in the second case, from the treatment plant, directly water is pumped to the distribution system without having a service reservoir. In this case, service reservoir is not available. So you pump straight into the distribution system. Like I told you, this is what is happening at Hafrel-Batin, okay? Hafrel-Batin town is divided into zones. So they pump directly from the treatment plant, you know, to the, okay, here also you can have a service reservoir at the treatment plant, or you may not have it, okay? You can have a service reservoir, or you may not have it. You can pump directly into the system, okay? And later in the last chapter, chapter 5, we are going to study the different distribution system, because the distribution system here is something else, okay? This is called a loop distribution system, okay? And we have what is called the open distribution system. You have the branch, which is the open, okay? The branch distribution system and the loop or closed distribution system, okay? This we will study at the end of the course, which is in chapter 15, okay? So now, to summarize, this layout, you know, summarizes everything we are going to look at in this course, okay? First of all, you have the reservoir. The reservoir receives input either as precipitation, that's rainfall, okay, or from runoff from river, okay? So we will analyze the water balance in chapter 2. Probably today we will start chapter 2, most likely, okay? And then again, it has to do with there may be some groundwater seepage and what have you, groundwater flow as well. Okay, there is a chapter on groundwater flow, and then there is the conveyance conduit. So, what are the fluid mechanics aspect? What is the hydraulics behind the conveyance conduit? Okay, with respect to the velocity, the flow rate, and all that. So, all this we will the subsequent chapters will treat each of the segments in greater detail. And the treatment plant, like I said, the treatment plant, we will not touch the treatment plant as per the design of the treatment plant, because that is the environmental engineering aspect. And like I told you initially, water resource and environmental engineering, they go hand in hand. They complement each other, okay? While water engineering is dealing with the flow rate, the velocity, and what have you, the quantitative aspect of the flow, the environmental engineering aspect is looking into the qualitative aspect, the quality of water. Does it need treatment? If yes, okay, what are the unit operations? What are the treatment processes that should be in place to change or to improve the quality of water? Okay, and this is where the environmental engineering part will come into, okay, from the simple physical treatment like sedimentation, like flocculation, you know, to other, you know, like filtration, to chemical treatment, you know, like disinfection and what have you, okay? And then if it is treated, it has to be pumped again to service reservoir and then to supply the city, okay? That is supply pipe to city. Now, design and capacity criteria for constituent structures, okay? First of all, what is design period? If you look at the bottom here, A, design period is explained, okay? Okay, it does not necessarily indicate the life of the structure. A design period takes into account other factors such as subsequent ease of extension, rate of population growth, and shifts in community and industrial or social development. Okay, so this is what make up the design period. That is the period within which the structure will be able to serve its intended purpose. Is that clear? So now, each of the various segments of the constituent structures, the layout, they have different design periods. So here we have like a table, you have the structure, the design period, and the required capacity, okay? The required capacity here is telling you which of the per capita usage do we use? Do we use the maximum daily, the average annual demand, or do we use the maximum hourly demand? Like I told you, each segment is designed using different capacity, okay, depending on which one is most suitable to be used, okay? So this is very, very important. This table is very important for you to understand it, because very soon after this, we will solve an example where the table will be applied in calculating the design capacity of the individual components of the water distribution scheme. So first of all, you have number one, source of supply. A, B, C. It can be river, well field, or reservoir. We all know each of these, okay? For river, it is indefinite, because I mean, river, most especially, I mean, a perennial. For river, you have two types. You have a perennial river, and you have intermittent or non-perennial river. Okay, the perennial river is one that flows throughout the year. Okay, and the non-perennial one is one that, you know, probably flows when during, let's say, the rainy season, when you have heavy precipitation, and then during the winter when there is no inflow, it dries out. Okay, but more often than not, you have rivers flowing throughout the year. So that is why their design period is usually indefinite. Okay, no specific time limit. And you have the well field, which is 10 to 25 years, reservoir 25 to 50 years. And then the required capacity. What per capita consumption do we use in the design for water intake? For river, we use maximum daily. For well field, we use maximum daily as well. And for reservoir, we use average annual demand. Here we mean maximum daily water requirement. We are talking about the water demand in this case, in this column, in the third column. Okay, we are talking about the water capacity. So here we use the maximum daily water requirement for river and well field, while for reservoir we use the average annual demand. You don't need to memorize the table, but you must understand the table in total. Okay, you must understand it in total, most especially the required capacity as well as the structure. For conveyance structure, intake conduit, this is the design period, and we use maximum daily. And for the conduit to treatment plant, we also use the maximum daily requirement, okay, which is the maximum daily requirement, water requirement for the population. For pumps, for low lift pump, this is the design period 10 years, and we use maximum daily plus one reservoir unit. Maximum daily plus one reservoir unit. Because the low lift pump will supply, is supposed to meet up the demand of the community for that day, as well as store water in the service reservoir. Okay, so that's why you have the maximum daily plus one reservoir unit. For high lift pump, which is the pump that is pumping from the treatment plant to the service reservoir, you use the maximum hourly plus one reservoir unit. Maximum hourly, because the high lift pump is the one that is pumping directly to the service reservoir. And don't forget, the service reservoir pumps, which is just a tank, an elevated tank in the downtown that allows water to go into the distribution system by gravity. Okay, it has to satisfy the maximum hourly demand of that community. Okay, the maximum hourly demand, and that maximum hourly is usually very high. Okay, and then the treatment plant, for the design of the treatment plant, we use the maximum daily water demand, and the design period 15 years, and the service reservoir. For the required capacity, to calculate the required capacity of the service reservoir, we use what is called the working storage. Okay, working storage. We'll explain how we find the working storage, okay, which is the storage capacity computation in section 13.10. Okay, so that will be explained later. Okay, but for in this case, the working storage will be provided for you. Okay, so you use the working storage plus fire demand for a specified duration, okay, which is in table 2, plus emergency storage. Don't forget, the service reservoir is the tank that supplies water to the distribution system, or to the population, or to the masses, to our individual houses. Is that clear? That is the service reservoir. So it has to take care of, you know, the working storage, okay, plus fire demand. Fire demand is the water required to fight fire. So, you know, in houses along the road, you have fire hydrants. Okay, even here in the housing, the faculty housing, you have fire hydrants. There are certain floors dedicated to the fire hydrant, so that in the event you have breakout of fire, you can quickly open the tap and water will gush out, so that it will gush in with such power, such that it will be able to put off any fire. Okay, so that capacity, that water needed for fighting fire, has to be incorporated in designing the capacity of the service reservoir, and then plus emergency storage. Emergency storage, I mean, sometimes you may have the need, to for any emergency purposes. Okay, just let's say safety factor in this case. Okay, so the service reservoir capacity is computed using three aspects. One, storage reserve, working storage. Okay, working storage, and then plus fire demand. Okay, and then for a specified duration, the fire demand has to be specified. The duration of the fire demand flow has to be specified. We will expatiate this in the example. Okay, plus emergency storage. Okay, so the service reservoir is made up of three components: working storage, fire demand, and emergency storage. Okay, and then we have the distribution system, and in the distribution system we have supply pipe or conduit. Okay, the supply pipe or conduit into the distribution system, and then we have the distribution grid. Okay, so here we design the capacity of the distribution system greater of 1 maximum daily plus fire demand of a day, or 2 maximum hourly requirement. So for the distribution system, you have two options. You have to look at which one is greater. Do you understand? Which one is greater? Is it the maximum daily plus fire demand, or the maximum hourly requirement? You choose whichever one is greater. Do you understand? You choose whichever one is greater to design the distribution system. Okay? Now, the average daily per capita usage for water supply. Okay? Average daily per capita usage for water supply. Here, public or municipal water supply include all domestic uses, commercial uses, this we explained before, small industrial uses, not having a separate system. Sometimes the industrial system, the industrial areas, they have their own separate supply, as we have seen in, last week in that diagram. But sometimes they also use the municipal water supply system. Then public uses by parks, buildings, treatment plants, and firefighting. And then we have to take care also of losses in distribution system. You usually have losses, which sometimes, depending on how good the distribution system is, it may vary, maybe 10 to up to 30% sometimes. Okay, maybe losses. And losses, sometimes you may be walking and you will see water just, gushing out from the soil. Okay, meaning you have maybe a faulty joint, or there is pipe burst and what have you that needs to be fixed. So usually you have losses in the distribution system. Okay, and the typical values or the percentage use is provided in the table below, table 1.2, depending on the use. For household, the average use in gallon per capita per day is 101, and the percentage of total is 56%. Okay, so meaning like this takes about 56%, and then for commercial, the average water use is 30, and it takes about 17% of the total water use, and the industrial 22 gallons per capita per day, which is its percentage is 12, public 17%, and its percentage is 9, and losses in the system about 6% here. Okay, so here 1 liter gallon is 1 gallon is made up of 3.8 liters. Okay, 1 gallon, because you have the UK gallon and you have the American gallon. Okay, and they all have different conversion units. Okay, now variations in usage. Okay, this I explained, but these are the we will provide some values, some important values here as well. There are 2 common trends here. The smaller the city, the more variable the demand. Okay, the smaller the city, the more variable the demand, and 2, the shorter the period of flow, Meaning for small cities, their demand is usually highly variable. By variable, mean it changes from time to time, okay, than for large cities, okay. And the shorter the period of flow, that's the shorter the period of flow of water, the wider is the variation from the average, okay, meaning the wider is the variation from the average. That is, the hourly peak flow is much higher than the daily peak. So here, the hourly peak flow is much higher than the daily peak flow, okay? Because the hourly peak flow has to satisfy all the requirements of the inhabitants of that city or that area, okay? The variations are commonly indicated in terms of the percentage of the long-term average value, okay? See figure 1.5, we are going to see it later. The maximum daily use. The maximum daily use is 180% of the long-term average daily use. Okay? And don't forget the average daily use usually is the annual one that we calculate over a year. Okay? So the maximum daily use is 180% of the average daily use. And the maximum hourly consumption in any day, the maximum hourly consumption in any day is likely to be 150 of the maximum daily use. Okay, so these are more or less, well, let's say, some correlation between the average daily use and the maximum daily use, and then another correlation between the maximum daily use and the maximum hourly consumption or maximum hourly use. Okay, so what we are saying is simple: the average daily use, maximum daily use is 180% of the average daily use, and then the maximum hourly consumption is about 150% of the maximum daily use. Okay. So if you look at it here, the one that is having the highest is the maximum hourly consumption, isn't it? Is the maximum hourly consumption. What about if I ask you now, how can you relate the maximum hourly consumption with the average daily usage now? What is the relationship? Work it out. What is the relationship now between the maximum hourly consumption and the maximum daily use? Yes, yes. Can you hear me? Guys, can you hear me?
Doctor, yes, we are hearing.
Yeah, so tell me now, what is the relationship? How do you relate them? The maximum hourly consumption with the average daily use. We know the relationship between the average daily use and the maximum daily, and we know the relationship between the maximum daily and the maximum hourly. Now, what's the relationship between the maximum hourly and the average daily usage? I give you just 2 minutes. 2 minutes to tell me, to work it out.
Doctor, the difference between maximum and average?
Yeah, between the maximum hourly consumption and the average daily use.
Maximum is what, like one day it's use the maximum, but average it's sum of all and
No,
divide.
mathematically, work it out mathematically. I need mathematical relationship. Yeah, mathematical. Like, if you look at this, maximum daily and the average daily, there is mathematical relationship, isn't it? Between maximum hourly and the maximum daily, there is mathematical relationship. So establish that and then get me the mathematical relationship between the maximum hourly and the average daily. let me see what you are writing. 1.5 times half plus 130, 180, 1 and 0.8 times of average daily. You know, what I want is this. Try to get my question. You see, maximum hourly use is 180% of the average daily usage. And then the maximum hourly consumption, which is this one, is 150% of the maximum daily use, which is this one. Now, what is the relationship between the maximum hourly consumption and the average daily use? It is a very simple relationship. I give you 1 more minute. Work it out again. 30%, no, 2/3. By relationship, I mean an equation. Like you tell me the maximum hourly consumption is 200, like let's say 100%, of the average daily use, or 200% of the average daily use, like that. So this is what I need. Okay. Oh, it's giving you a hard time. Ya Shabab. Is Mihmas around? One guy is still absent today. Hamdan is here. Muhammad Bashar, what is your answer?
I think it's wrong.
It's wrong. Okay,
Maybe,
let me.
I'm not sure.
Okay, let me explain it here so that let me work it out. Let me work it out for you. The maximum daily use is 180% of the long-term average daily use. So if I represent the maximum daily use as MDU, is 180%. 180% is 1.8, isn't it? Of the average daily use. If I represent the average daily use as ADU, okay? So MDU is equal to 1.8 ADU. Is it clear?
Yes, Doctor, clear.
Okay, now, based on the second statement, it says the maximum hourly consumption in any day. So let me represent the maximum hourly consumption as MHC is equal to 150% of the maximum daily use. 150% is 1.5, isn't it? Of the maximum daily use. Maximum daily use is MDU, correct? So now, what is MDU? MDU is 1.8 ADU. So 1.5 times 1.8 ADU, correct? From here, isn't it? Now, the maximum hourly consumption, 1.5 times 1.8 is 2.7 times average daily use. And 2.7 in percentage is what? 270% of the average daily usage. Do you understand? So the relationship now between maximum hourly consumption and average daily use is that the maximum hourly consumption is 270% of the average daily usage. Do you understand? Do you understand this simple, relationship? Okay, good. Abdulaziz, you said 2.7. So, Abdulaziz, do you write your 2.7 after I finish my analysis? Abdulaziz of the Fury. Before, okay, good. So Abdulaziz got it right in that case. Okay, so let's move on. But I hope it is clear to you. Now, this is the typical variation in usage in a day. Okay, this is the percentage of average of daily average water demand. Okay, from midnight. It goes down, it goes down early in the morning, and then it begin to increase. You see 6 to 8, it's increasing because everyone is preparing to go to work around 8, okay, time of the day, and then it declines around 12, okay, and then in the evening around 6 to 8 again, it goes up, okay, and then down into the night, it goes down. This is the water demand, the average daily variation in water usage. Okay. Now, let's take this example. Here there is equality sign. Okay, here also there is equality sign. All right. Now, this example saying for a city having an average daily water usage, average daily water usage of 150 gallons per capita per day from the municipal supply, determine the maximum hourly requirement, excluding the fire demands. So this we were given here, what we were given here is the average daily usage, which is 150. We are asked to determine the maximum hourly requirement. We just found out that the maximum hourly requirement is what? Is 270 percent of the maximum daily. Okay, so all we need to do is to first determine the maximum daily, okay, which is this one, okay, which is 180% of the average daily. So 180% of the average daily, which is 150, okay? So this is 270 gallons per capita per day. And then we now use for a maximum day, maximum hourly usage is what? 150 of daily use, okay? Or of the maximum daily use, okay? You can do it in also one step. That is using the formula we derived. That is using just the the average daily, okay? That is the maximum hourly, the maximum hourly requirement or usage is equal to 2.7. Okay, it's 2.7 times the maximum, 2.7 times the average daily. That is times 1.5 times 150. Okay, so this 2.7 times 150 will give you what? Will still give you 405 gallons per capita per day. Okay, so meaning you can do it in one step as I did. Okay, but in this case you have to use the relationship between the maximum hourly and the average daily. Okay, otherwise you'll have to take it in two steps. That is to determine the maximum daily using the relationship that is 180 of the average daily, and then determine the maximum hourly using the relationship that it is 150% of the maximum daily. Or you use the maximum hourly requirement is 2.7 times the average daily. Okay, and you will arrive at the same answer. Okay. Now, fire demand. I explained what fire demand is meant for, okay, which is the quantity of water included for fire purposes under the category of municipal use, okay. The fire demand comes under the category of municipal use, okay, and it's quite small, but the rate of withdrawal is high, okay. It's quite small, the amount, the total quantity is small, but the rate of withdrawal is high, meaning the flow rate, okay, at which it is supposed to gush out should be very high, because fire, you need to have flow rate such that it will be able to rise up to certain number of story buildings. Let's say 2-story building, 3-story building. Okay. The distribution system and service reservoir thus should incorporate provisions for fire demands in their capacities. Okay. So we should incorporate the fire demand in designing the distribution system, the service reservoir. Buildings are classified based on the type of building material and the fire resistance rating. Okay, because each material, it has different fire resist. Each building material has different capacity to resist fire. Okay, and there is fire resistance rating, which we are going to learn. The fire resistance rating is defined as the time in hours or fraction thereof that a material or assembly of materials will withstand the passage of flame and the transmission of heat when exposed to fire under specified conditions of test and performance criteria. So, in summary, what we're saying as the fire resistance rating is just the period within which a material can withstand, meaning can tolerate flame. Flame here is fire, isn't it? Can tolerate flame or transmission of heat when it is exposed to fire under specified conditions. Okay, that is the fire resistance rating. What are the types of construction materials? Types of construction and flow area. Here we have types 2B, 3B, and 5B. These three types have no fire resistance rating. The majority of private homes belong to type 5B. They have no fire resistance rating. Okay. The fire area is the total flow area in square feet of all flow levels. All flow levels, meaning you can have two floors. If you have two floors, you will have to add ground floor and the first floor. Okay. So the fire area is the total flow area in square feet of all flow levels under the horizontal projection of the roof of a building, excluding the basement. Okay, excluding the basement. For most development projects, the building with the largest fire flow determines the requirements for the entire project. Okay, the building with the largest fire flow determines the flow requirements for the entire project. Why do we choose the building with the largest fire flow? If it has the largest fire flow, then that means it will need the most amount of water. Okay, so if you will be able to take care of the building with the largest fire flow, then definitely you should be able to take care of buildings with less fire flow, isn't it? But if you base your design on the fact on buildings with less fire flow, then your fire requirement, your fire demand will not be able to take care of buildings with largest fire flow. Is that clear? Okay, so here is a simple design criteria which you all know. I mean, you have taken probably some design courses, maybe in structures. We design for the worst case scenario, okay? For the worst case scenario. So that if we can take care of that worst case scenario, then definitely we can take care of milder cases, cases that are not worse, okay? But if we don't design for that worst case scenario, then there is problem. It means whenever we have such worst case scenario, then our system cannot stand. Is it clear? Now, this is the table 1.2, which has the minimum required fire flow and flow duration for buildings. Okay, this is table 1.2, which has the fire area in feet square, and you have the conversion if you want to convert it to meter square. Okay, you know, 1 feet 0.3048 meter, 0.3048 meter, 1 feet, 1 foot, 1 foot. Okay, so here you have type 1A and 1B. Okay, these are the different types, and you have the fire flow in gallons per minute. Okay, if you want to convert it to liters, you have times 3.785, or okay, for liter per minute. And you have the flow duration. It is 2 hours, 3 hours, okay, 4 hours. So the values you have here are the flow areas. Okay, all the values you have here are the flow area, the fire area. Okay, so more often than not, the fire area will be provided, and we explain how the fire area is computed. Is the total flow area in square feet of all flow levels under the horizontal projection of the roof of a building, excluding the basement. Okay. So we will take 5 minutes break, and when we come back, we will take example on how to calculate the fire demand and how to design for the different components of the water of the water system, okay, of a water treatment or water supply system. Okay. So
Okay,
let's take 5 minutes. Yes.
Okay, doctor.
All right. So see you back in 5 minutes. Yes, gentlemen, you back?
Yes, doctor.
All right, so let's move on. All right, so here we have the minimum required fire flow and flow duration for buildings. For instance, if your flow area, let's say it's 22,000, most of the, or let's say it is 9,000, most of the residential buildings we have fall under type 5B, under this, okay? Let's say your calculated flow area is 9,000. 9,000 falls in this range between 7,700 and 9,400, okay? So it is on this line, okay? So what do you use? What flow, fire flow do you use? You use 2,500 gallons per minute. And what is the flow duration? You use 2 hours, okay? Let's take example and demonstrate that. Here, example 1.7 says a city with a population of 20,000 average daily usage. Average daily usage. You need to underline that, okay? Average daily usage. Okay? Is it the maximum daily use? Is it the maximum hourly consumption? Okay, but this is the average daily usage. Okay, very important. So the average daily usage of 150 gallons per capita per day. The fire demand is dictated by a 3-story building, each floor of which 3-story building. Okay. 3-story building. Each floor is dictated. Each floor of which has an area of 2,400 feet square. Feet square of ordinary 5B construction. Okay, determine the fire demand and the design capacity for different components of water supply project. The working service with storage is 1.5 million gallons per day. Okay. So first, we have a population of 20,000. Okay, and the fire demand is dictated by a 3-story building. Each floor of the building has an area of 2,400 feet square of ordinary 5B construction. Okay, we are to determine the fire demand, which is the first part, and the design capacity of different components of water supply project. The different components, from the intake to the treatment, low lift pump, high lift pump, service reservoir, and then the distribution main. Okay, that is the conveyance conduit. And we are given the working service storage, which is 1.5 million gallons per day. That is the MGD. That is million gallons per day. Okay, now let's start. The first thing here, you see, we were provided with the average daily usage. So we need to calculate the maximum daily usage and the maximum hourly usage, because we have these 3 different types of usages: average daily usage, maximum daily usage, and the maximum hourly usage, because we will use this in the design of the different components as per this table. You see this is using maximum daily, average annual demand, maximum daily, maximum hourly. Okay, so all the 3 types of the water demands are present here in the design of the constituent structures. Okay, so we were given the annual average demand, so we need to find the maximum daily demand and the maximum hourly usage. Okay, which we calculate using the relationship. The maximum daily demand is 180% of the average daily, and then the maximum hourly demand is 150% of the maximum daily demand. Okay, so we start with this. Okay, maximum daily usage is this. Okay, this is 150. So the maximum daily is going to be 180 times 1.8 times 150, which is 270. Okay, and the maximum hourly demand is going to be either 150% of the maximum daily or 270% of the average water demand. Okay, so this is how we obtained 405. Okay, it is so simple. Okay, this is 1.8 times, I think the value provided is 150 times 150. And this one was obtained by saying 1.5 times 270, or you can say it's 2.7 times the average daily, which is 150. You will have the same answer. Okay. Now, the average daily draft, that is the draft here, is referring to the withdrawal, the usage, but by the population. Remember, the population is what? 20,000. The city has a population of 20,000, and each person has an average daily use of 150 gallons per capita per day. So what is the total daily use? What is the total average daily use of water by 20,000 people? Okay, so this is what we are going to find here using the average daily draft. Okay, and of course here all we did is to multiply the population by the average daily use, which is 150. Okay, but because we want to convert it to million, here given in gallons per capita per day, so if you multiply by the population, we will have in gallons per day, and that will be, we want to convert it to million gallons per day, so that's why we divide by 1 million. Okay, ordinarily we just multiply the population with the average daily use, which is 150 gallons per capita per day, to have it in gallons per day. But to convert it to million gallons per day, that is why we divided by 1 million. You understand? The average daily draft is 3 million gallons per day. The maximum daily draft, we now use the 270. Okay, the same thing, multiply by the maximum daily usage over 1 million, 5.4 million gallons per day, and the maximum hourly draft, we use 405, which is the maximum hourly usage, times the population over 1 million, which is 8.5 million gallons per day. Okay, now let's calculate the fire flow, which is the first part, because we will use the fire flow in determining the design capacities of some of the components, like the service reservoir, like the conveyance conduit. Okay, so we will need the fire demand. So let's find the fire demand. And the fire demand here, we have 3-story building. By 3-story building, you know, you have the first story. We exclude the basement, so we don't include the basement. That's the ground floor. So we start from the first floor, second floor, third floor. Okay, so that is the 3-story building. If it is just like a duplex, okay, so that is 1-story building. This you need to understand. Okay, we exclude the basement, that is the ground floor. Do you get the point? Okay, so 3-story building here, the total floor is 3 times each floor has 2,400. Okay, so this is the total floor area, 7,200. So we now go to that table. We know to determine the fire flow and duration, our area is 7,200. The building, the type is type 5B. So why is the area falling? 7,200 falls here, between 6,200 and 7,700. So we now go ahead to determine the fire flow, which is 2,250 gallons per minute, and the duration is 2 hours. Okay, so let's go back. Okay, you can see that 2,250 gallons per minute, or in million gallons per day. This is gallons per minute. If you want to convert it to million gallons per day, it will be in 3.24. Okay, million gallons per day. And how do you do that? This is gallons per minute. So the first thing you do is to convert it to gallons per day. And then when you convert it to gallons per day, you divide by 1 million, and that's it. Okay, and you know how to switch between per minute, to change minute to day. Okay, 1 day is made up of 24 hours. Each hour is made up of how many minutes? About 3,660 by 60s. Okay, each hour is made up of 60 minutes. Okay, so 24 by 6 by 60, that gives you the number of minutes. So 1 over that. Okay, so I hope you reach. Okay, between gallons per minute to million gallons per day. I hope you will not have an issue there. Okay, it is simply, let me try to do it here. This is gallons per minute, and then the same gallon. Now 1 minute is 1 over 24 hours in a day times 60. So this will go up and multiply this, okay? And then you divide by 1 million. Okay, so when you do this, you will arrive at this value here. Okay, now maximum daily plus fire flow, because in one of this table, let me go back, you have one having maximum daily plus fire flow. Yeah, maximum daily, you know, to design the distribution main, you need greater of maximum daily plus fire demand of a day, or maximum hourly requirement. So we need to determine the maximum daily plus fire demand so that we can compare it with the maximum hourly requirement. Whichever one is greater, we pick that and use it for designing the distribution system. Okay, so that is why we are determining this particular aspect here, the maximum daily plus fire flow. The maximum daily is already computed here. The maximum daily draft is computed here, 5.4, okay, plus the fire flow, which is 3.2, okay, so altogether 8.64 million gallons per day. Now we'll go and look at all the different components of the water supply layout, okay, starting from the pumps. Okay, we have two pumps, low lift pumps, high lift pumps. Okay, assume that the required capacity or the required flow is handled by 3 units and that one reserve is installed. Normally for the pumps you have more than one working simultaneously. Okay, so here we are assuming that the required flow is handled by 3 units, meaning you must have 3 units for you to be able to pump the required flow. But then at the same time, you always have reserve in case you want to take out any one of them for service or there is any breakdown. Any of the pumps has broken down. Okay, so you must have a reserve unit. So we are assuming that is to be handled by 3 units and then 1 reserve unit is installed. Altogether, here we have 4. Okay, altogether we have 4, out of which 3 are the ones delivering the required flow. Okay, so for the low lift pumps, we now have 4/3 of the maximum daily. Okay, here is equality sign. So this is the maximum daily draft, 5.4, which we already calculated. Okay. So all together, we have 4 pumps, out of which 3 are working. So 4/3 times the maximum daily. Okay. Because for the low lift pump, we design it using the, if you check table 1.1, design it using the maximum daily plus 1 reserve unit. It's specified that we have to use 1 reserve unit for the low lift and the high lift pump. Okay, for the low lift we use the maximum daily, and for the high lift we use the maximum hourly. Okay,
Doctor, from where
yes,
did you get 4/3?
yeah, why 4/3? Because ordinarily we want to increase the flow of the flow rate. The maximum daily flow rate will be taken care of by the 3 pumps. Do you understand? So the capacity of the 3 pumps should be equal to the maximum daily. Do you understand? But we are using 1 reserve unit because we want to determine the capacity of the low lift pumps. Do you get the point? So that is why we put 4/3. 4 over 3 here, if
Yes.
we have 3, that is just 1, isn't it? So that gives us the maximum daily, which will take care, that flow will be taken care of by the 3 pumps. But how do we determine the additional pump? Okay, so that's why we use 4 over 3 times the maximum daily, because 4 over 3 is going to be more than 1. Is that clear? 4 over 3 is 1.33. It is 1.33. So now the required capacity of the low lift pumps is now going to be 7.2, not 5.4, because the difference that is 7.2 minus 5.4 is 1.8, isn't it? That 1.8 is for the reserve unit, is for the capacity of the reserve unit. The 3 low lift pumps will take care of the maximum daily required 5.4. Do you understand? But we want to know, okay, this is the capacity, million gallons per day, 1.8. Okay, so now 1.8. So how do we get the point? Because pumps are sold based on the capacities, okay? It is based on their capacities. So how do you determine the capacity of the pump? Do you get the point? We are to use 3 at a time, but we need to have 4 so that we have 1 as standby. Do you get the point? So that's why we are saying 4 over 3, so that we determine the capacity for all the 4 pumps, not just 3. For 3, the 3, they should be able to pump 5.4, but we don't need that, okay? We need to determine the capacity for all. Alternative way to do this is to say, okay, the 3 pumps will deliver 5.4, correct? 5.4 million gallons per day. So 1 pump will deliver how many? Will deliver 1.8, correct? So, so in that case, 4 pumps, if 1 pump will deliver 1.8, then 4 pumps will deliver what? 4 times 1.8. 4 times 1.8, which is the same thing as 7.2 million gallons per day. Do you understand? So these 4 of these don't get confused. It is very simple. You know, the 3 pumps should be able to deliver the total maximum daily demand, okay, which is 5.4. So if 3 pumps deliver 5.4, so 1 pump will deliver 1.8, isn't it? Because it's going to be 5.4 over 3, correct? So if 1 pump delivers 1.8, then 4 pumps will deliver 4 times 1.8, which is 7.2. So this is how we got the 4 over 3. Do you get the calculation now?
Doctor, it's clear.
Yeah. All right. Let me check if you wrote anything. Okay. Now, the same thing for the high lift pumps. But for the high lift pumps, if you check table 1.1, to calculate the required capacity, we use the maximum hourly. Maximum hourly plus 1 reserve unit. Okay. So the same thing we have for the maximum hourly. This we found before. Maximum hourly draft is 8.1, isn't it? So 3 pumps are to deliver 8.1. So 1 pump will deliver what? 8.1 over 2. Sorry, 8.1 over 3, which is 2.7. So 1 pump will deliver 2.7. Okay. What about 4 pumps times 4? 2.7 times 4, which is 10.8. Okay. So this is, you know, the explanation of why you have this 4 over 3. Do you understand? Now, let's move ahead. This is for the pumps, the low lift pumps and the high lift pumps. How do we get the design capacity to use maximum daily and hourly? We go to table 1.1. Is that clear? Where we have the structure, design period, and required capacity. That is where we go and look at, okay, what required capacity do we use? Is it the maximum daily, maximum hourly, or is it maximum daily plus fire demand, or, you know, whatever it is, it's provided in table 1.1. Now we move to the service reservoir. Okay, for the service reservoir, if you check table 1.1, we are to use working storage plus fire demand for a specified duration plus emergency storage. It has three components. Okay, the service reservoir has three components. First is the working storage, okay, and then fire demand for a specified duration, and then emergency storage. Okay, so let's start with the fire flow. The fire flow duration is 2 hours. This we got from the table. Okay, so within 2 hours, what is the total fire flow? Okay, the total quantity of fire flow, okay, in a day. So it's going to be 2/24 times the fire flow which we computed here. Okay, this is the fire flow 3.24. Okay, but 3.24 million gallons per day. Okay, but based on the duration, it is expected like when you have a fire, it takes like maybe 2 hours to put off the fire. You don't use the 24 hours. Is that clear? So that is why we use 2/24. Okay, this is 2 hours per day, and this is 24 hours. Okay, so in a day we use a fraction. Okay, so 2/24 times the total fire flow to get the total quantity of fire flow. And then the working storage has been provided from the question. The working storage has been provided to be 1.5 million gallons per day. So now, like I said, the service reservoir has three components: the emergency storage, the working storage, and the total quantity of fire flow. Now, the emergency storage. How do we calculate the emergency storage? We calculate the emergency storage by having some days, okay, multiplying using the average daily draft to increase, okay, by multiplying with some number of days, so that like even if you have say any emergency maintenance system at the treatment plant, that you have short in supply of water to the service storage, you should still be able to supply the town for some days. Okay, so that is why you have the days here times the average daily draft. So here we assume like 3 days. Okay, so like even if there is no inflow into the service reservoir, the service reservoir should be able to supply water to the town for like 3 more days uninterrupted. Okay, so that any problem at the downstream side at the treatment plant can be fixed within that time and supply can be reinstated. Okay, so that's why, so the emergency storage is the number of days times the average daily draft. Okay, we found the average daily draft before to be 3 million gallons per day, so we took 3 days. Okay, 3 times that, we get it. And then the service storage, now I said it's made up of 3 components. The first component here is the total quantity of fire flow. The second one is the working storage, which is provided from the problem. The last component is the emergency storage. You can see the emergency storage is really very high. Okay, it's really very high because that storage will translate into having a very huge tank. Because total now you have 10.77 million gallons per day. Okay, 10.77 million gallons per day. Okay, now the design capacities, this is the total. If we go to the distribution system, we have greater of 1 maximum daily plus fire demand of a day, or maximum hourly requirement. Okay, so which one is higher? The maximum, we have to compare the maximum hourly requirement 4 and 6. Which one is higher? This is 8.1, this is 8.64. So the greater one, which is 8.64. Okay, so for the distribution system, we pick 4 or 6, maximum hourly draft or maximum hourly plus fire flow. Okay, so we pick 8.64. So for the distribution system, we pick the one that is greater, which is 8.64. Okay, so the total result is provided in this table here. The river flow, okay, the river flow is provided with the max. It has to be based on the maximum daily. The maximum daily is 5.4. This we found before. Then the intake conduit. This is based on table 1.1, okay? The intake conduit, that is conduit to the treatment plant, okay, is based on maximum daily, 5.4. Low lift pumps, maximum daily plus reserve, 7.2. This we found. High lift pumps, which is maximum hourly plus 1 reserve, 10.8. And treatment plant. The treatment plant is based on maximum daily, which is 5.4. And the service storage, which is based on working storage plus fire plus emergency, which is 10.7. Then the distribution system, which is maximum daily plus fire or maximum hourly, whichever is greater. So we compared the two and realized that the maximum daily plus fire demand is greater. So we pick the one that is higher, okay, which is 8.64. Okay, so this is the final table of the design capacities. Okay, of course, it doesn't stop from here. From here now, like for the pumps, you go and find the pumps that will satisfy this flow rate. Okay, for the treatment plant, you design all your treatment. You know, Dr. Bashir will do about the inflow rate, isn't it? So this will not be the inflow rate into the treatment plant. Okay, and then the service storage, okay, which is this, and then the distribution system. This is the inflow into the distribution system. This we will take care of in chapter 15 when designing the distribution system. Okay, any question? Is it clear? All right. So now industrial requirements. You see here we are talking about municipal requirement, municipal supply. Okay. Okay. So okay, it's clear. All right. So we did not include any industrial requirements here because more often than not, I told you industrial, you know, water requirement, they need huge amount of water, and some more often than not, they have their separate sources. Okay, but sometimes depending on the water use or water requirement by the industry, they may use the municipal water supply. Okay, so the industrial component within municipal water supplies does not include water. Large water using industries, okay? For large water using industries, they all have their separate water supply scheme, okay? For the most part, such large industries supply their own water. Okay, this I just explained. The single largest water user is the thermal power sector, okay? The thermal power sector is the largest water user, okay? So these are, this table 1.3 gives requirements of major industries, okay? Thermoelectric, power, the average water use, okay, steel, paper, organic materials, petroleum, refining, plastic, and cement, okay. Now, waste dilution requirements. In earlier times, by waste dilution here, it was a common practice to dump raw municipal and industrial waste into the same river that served as the source of supply. But you go down downstream. Okay, you extract the water upstream, use it, and then dump the waste downstream, okay, into the same river that serves as the source of supply, thus relying on the self-purification properties of the stream. Okay, self-purification, as water flows, you know, it's exposed to oxygen. Oxygen dissolves in the water, and whatever waste you have, bacterial waste, they utilize the oxygen, and then the waste gets automatically treated due to the turbulence and the dissolved oxygen that is present. Okay, and the aquatic life, the pathogens, the bacteria, so they feed on the waste. So the waste becomes automatically treated. Okay, Dr. Bashir will still teach you about the wastewater treatment. Okay, most especially the biological treatment of wastewater. Okay, which utilizes bacteria to feed on the waste. It will feed on the waste, thereby reducing it. Okay, by feeding on the waste, it oxidizes the waste. Okay, it reduces the waste from harmful substances to less harmful substances. Okay, so this takes place in wastewater treatment plant that utilizes biological treatment plant, biological treatment process, and also it takes place in flowing stream. Okay, as the stream flows, it absorbs oxygen from the atmosphere, and the bacteria inside the water now utilizes the dissolved oxygen to feed on the waste and then getting the water treated. This is the summary of the self-purification. Okay, as long as the stream flow is at least 40 times, okay, as long as the stream flow is at least 40 times that of the waste flow, and there's sufficiently long reach of river to the next city, both nuisance and unsafe conditions can be avoided. Meaning, when you dump raw waste into river, okay, as long as the quantity, okay, of waste water flow is so small compared to the stream flow, then the river, the stream will be able to, take care of that waste. It will be able to treat it conveniently, as long as you have long distance of travel time, okay, between the point where the discharge of the wastewater is taking place and the next city, so that the next city will not use, polluted water as its source of supply. Okay, for average conditions, it has been found that thoroughly treated waste for municipal and industrial sources, excluding thermal power plants, requires a ratio of stream flow to waste flow of 2. Okay, that is for average condition. Okay, the thoroughly treated waste from municipal, that is if the waste is treated. The first instance of using ratio of 40 times is if the waste is untreated. If it is treated, then you only need a ratio of 2, stream flow to waste flow. Okay, so the flow rate will of the stream should be just twice that of the waste flow. Okay, that is if the waste is treated. See figure 1.6. So requirements for waste dilution. Okay, so this is the ratio of stream flow to waste flow. So if there is percentage of treatment, when there is no treatment, zero treatment, the ratio is 40%. If there is treatment up to 90%, it reduces, okay, up to close to 95%. So that is when it reduces to about 2. Okay, the ratio becomes 2. Okay. Oh, this is the end of the first chapter. So study it very well. Okay, so that next class, we will have our first quiz, and then the week after, we will have a second quiz, because our quiz is supposed to be every 2 weeks. And I will suggest that unless it is absolutely necessary, we don't postpone the quizzes. Okay, the quizzes are meant to make you read, to force you to go and read those sections that we covered within the time frame. Okay, but if you accumulate the sections, you accumulate them, that is when you will not have enough time to read thoroughly and understand and then do well during the quiz. And all our quizzes will be taking them during the lab period. Okay, meaning before we start, we'll take our quiz within, let's say, just 10 minutes, 15 minutes, and then we start our lab. Okay, so all our labs will be physical. Okay, so please get ready for the quiz. Okay, next week our lab is going to be physical. This week our lab, we will do it online, but next week you are supposed to come to the lab at 2, and it will be conducted. We'll take our quiz first, and then we now take the lab session. Okay.
Doctor,
Yes.
the quiz is gonna be what, Doctor?
Pardon?
The quiz is gonna be next week, yes?
Yes, it's going to be next week on chapter 1.
Or
Yeah, on chapter 1, because we just
Okay.
finished chapter 1. Yeah, so it is a good avenue for you to read the whole chapter, understand it, and digest it. Very soon we'll begin to talk about major 1, which is coming in week 6. So the earlier you start reading very well and very hard, the better for you. Don't wait until it is time for the exams that you'll be running helter-skelter, reading here and there. Start reading very hard from day 1. when it's time for quiz and for majors, you won't, waste a lot of time. Okay, read well ahead of time. This is the best strategy, really. This is the best strategy. And again, for all quizzes, read as if that is your final exam, meaning take your time, digest the material, understand it. If you have any question, we already have our WhatsApp group. Feel free to send me a message or whatever that is not clear, and I will oblige. Okay? All right, so what will happen today? We will meet again online. We will meet today online at 2, okay, to start the lab. But then let me explain something very important. More often than not, because of the voluminous nature of the course, you can see that the course has many chapters, very huge, the textbook, very big, a lot of things to be covered. So usually I may be taking some few minutes, probably maybe up to an hour of the first hour of the lab to cover some aspect of the theory before we begin the lab. Okay. So this is very, very important so that we will be able to cover the syllabus as spelled out, okay? Because the 2 hours allocated, for the theory is actually very, very short for us to be able to fully cover all the chapters, all the sections that are present in the syllabus, okay? So if you don't have any question, see you at 2 o'clock. I will post the lab manual on the blackboard, okay? All right. Ma salama.